Okay. How's it going? Good. Yeah? What's good? Huh? It's the day. It's a little wet today, but a little bit warmer yesterday. Beautiful. I mean, well, it's a little overcast, but compared to some of the cold we've been experiencing, it's been very nice. Any other interesting things going on? Hanging in there? Okay. Is it midterm season now? Yeah. Kind of? Alright, well, I think you're going to like what's happening in this class. We're going to, it lightens up a little bit in terms of the post-lab exercises. Okay, but now we have, of course, the group projects that are ramping up. Okay, and some of these, I may need to change some of the deadlines for some of the labs, so that, so like sometimes in a couple of the upcoming labs, we actually have them kind of combined, like it's just one assignment. So it won't be due necessarily at like 4 p.m. the day. Okay. Any questions about the group projects? Tomorrow by 5 p.m., what needs to happen? The pre-proposal needs to be in, correct. And what are some of the elements that you are including in the pre-proposal?
What kind of physics are you using?
Yeah.
Using your group?
Using your group? What's that?
I don't remember any.
Okay, yeah, no. So have you submitted it already? No? Okay. Who submits it? Everyone, right? It can be identical between the 3 members of your team. That's okay, but you all need to submit it individually. And there's a peer evaluation. Has anyone completed it? Is everything? Yes. Did it all work okay? Yeah. Was it straightforward? Okay, good. Good. Oh, okay. So, what was that? Additional feedback?
I said I gave them all 0 and me 30.
Oh. Yeah, I don't know how to. I haven't quite figured out how to compensate for narcissism in the algorithm, but maybe we can discuss that if it becomes an issue. All right. So thank you. So please do that by 5 p.m. tomorrow. It's not that difficult. I'm not going to grade it very harshly, and I am going to go through them. So you'll be getting feedback from me, for better or worse. Okay. And so I would appreciate you getting that in so I can start giving everybody feedback. All right. Maybe the most feedback you get from me, to be honest, until the end of the class, because I think it's kind of important to get the initial conditions correct. Okay. Anything else? How's ANSYS going? Okay, slow. Like in which respect slow?
Computer-wise.
On your computer or the lab computers? On your computer, okay. So this brings up a point. If there are those of you who do not have a PC, for one, okay, or that a Mac with parallels is not cutting it, your tuition is covering those labs in some part, so I think the machines there should be pretty good. Have you noticed anything about what happens when you do work on your own computer and then you take it over to the computer cluster or to your friend's computer or anything like that? Okay, well, I don't know if I explicitly stated it. There's a good way to export your file, right? So as you probably know by now, when you save your work, it creates files and like a directory and all this kind of stuff. You can have it export to just like one file. That does make the transfer to another machine more straightforward, I guess. Or you could just copy the file in the folder, right? But I don't know. So are we technically? I'm asking for feedback here because if the computers aren't working, or if we have issues, we can ask the people in ECS to help us out. Yes.
I think multiple people run into this issue where you can't reset your password on the like it just keeps failing.
Okay. So go ahead. Yes. So, okay, yes.
I could see yesterday you would go to the ECS website and you fill out like a ticket and they for me resolved in like 2 hours. Like they responded, how they will log in.
Yes.
So,
Yes, and so I did receive that feedback from a couple people. I actually submitted the ticket for them, and then it was resolved very quickly. If you have that issue, yes, you can go to me, but then you've got one more layer, or you can just go to the ECS Rutgers website, and they'll take care of it for you. Okay? Thank you for bringing that up. Okay? They were very responsive. I knocked on their door though. And I said, it is an issue, so that it was resolved within minutes. Okay? Anything else? Okay, good. Very, very good. Do you like still getting to do MATLAB and ANSYS together? Yeah? Okay? I mean, hopefully that's going okay. And of course, we still have office hours. TAs Mondays and Fridays, and I have office hours before class on Tuesdays and after class today at 3:45. I just need some time to get back to the office. Okay. All right. So what are we going to cover today? We are going to discuss a little bit about mechanics, a little bit about fluid mechanics, and then the finite volume method. And once again, any one of these topics, mechanics, fluid mechanics, or finite volume method, could be a very extensive course. So we're going to be doing our impressionist painting, okay, of this topic. And hopefully it'll give you an appreciation for what is involved and what is going on in ANSYS and in Fluent. Okay. Reminder or review, what did we cover last time? Covered finite element method. And I think maybe there at least was maybe some appreciation that the finite element method has a lot of moving parts and there's a lot more math going on. And so you use the finite element method, or you're using it, I guess, in your post lab that we do as well, to make some comparisons between the finite difference, or to compare it to the finite difference methods that we implemented in MATLAB. And something to keep in mind is that the number of elements that you have when you use either of these methods, finite difference, finite element, or any of these methods, if we talk about finite volume too, can be dependent on not just the geometry, of course, but the physical parameters. So when you change the turkey material, right? So right now we've been still looking at square turkeys. Okay, we're almost done with our square turkeys. When we change the material from turkey material to copper, it's very possible that the number of required elements to get an accurate answer could be significantly reduced. Okay? Significantly reduced. Well, why would that be? Well, we've talked about if you have a high thermal diffusivity, right, then the heat can kind of just move through the system very quickly. You can get to equilibrium very quickly. And so if you don't have much of a gradient, right, in other words, if the distribution is pretty even across the turkey, or the square turkey, or whatever it is, or the copper plate now, or the copper box, then it's possible that, you don't need very many elements. Has anyone done the assignment and kind of know what I'm getting at? Okay, well, all right, when you do the assignment, keep what we just said in mind. I'm trying to help you out, okay? All right, so here we go. We're going to review these three things: mechanics, fluid mechanics, finite volume method. And I understand fluid mechanics may not be a review. Of course, we're not really reviewing finite volume method. We're kind of just pressing it down. So this is a blast from the past. If you took mechanics with me, and you're asking why are we talking about stress? This is not supposed to be a mechanics notation, and then our method of choice here is of discussion today is the finite volume method. So also dealing mostly with fluids. We're going to have stresses. All right. And so, what are your options for stresses? But like, what are the stresses we talked about in mechanics and materials? Yes, Andrew.
Shear stress.
Okay, we're talking about shear stress. Okay, and we had the towels with the subscripts. Okay, so we're going to show a lot of that. We're just kind of breeze through, but this is kind of almost like a discussion at this point. What's the other type of stresses that we have? They say axial, normal stresses, right? Okay, so in a fluid system, what do you think axial stresses will represent? How do we translate those normal stresses to a fluid system? What are they? Yes. Sure. Right. So pressure, and when we were talking about pressure, now we've got essentially three stresses that are all the same: sigma x, sigma y, sigma z. Right. And so we're talking about we can break these things down. Like on a given surface, you've got some type of traction vector or force involved with it, right? And we're taking over a small area, and we're going to say that, this is review, right? Go through this whole business, right? We're going to say that we have these different components, and the normal components would be like a sigma z, right? And that's just going to be a sigma z. And then in a fluid, that's just going to be a peak. And sigma z will be equal to sigma y, and will be equal to sigma x. Okay? So this is just kind of trying to make some parallels between what we've talked about, okay, in the mechanics world to the fluids world. And yes, we talked about how the first subscript is usually going to be describing the direction of the face, and the second subscript is going to be describing the direction of the stress. So now shear stress is that this is kind of usually the more annoying one, and it comes up a lot. Right, you've seen this. This is just kind of quick review of everything that you remember there. Okay. Shear stress, right, could be like tau zx, tau zy, could be a tau xy. These types of things. And we've talked about equilibrium when it's a solid. Okay? Moments in these various things, right, going on. It gets a little bit different in a fluid. Second. Okay? But one of the things to keep in mind is that when we're dealing with fluids, when we're dealing with solids, we can still come up with a tensor. Okay? And what essentially is the tensor? Do you remember what tensors are? There, but how would you describe a tensor? Sure, Federico.
I would describe it kind of like a generalized form of like the order of like elements within one element of the thing. So like a vector, like a scalar first order tensor, vector second order, or a matrix is like a third order. That's how I thought of it.
Okay, so at a given location, so this is a little bit painful, some of the feedback. I mean, when you see the feedback in reviews from classes, sometimes it's a little painful. And one person wrote back, I still don't know how to describe the stress at a given location in a solid. After the whole class. It's like, ugh. Okay, like the idea of coming up with this state of stress at a given location was still, I hadn't quite gotten that point across. So how would you help someone understand that? And you can also use the word tensor in there. How would you help someone understand? I've got a structure, or now I've got a say what we're talking about or how you describe the state of stress at a given location. Yes.
It's like a nice, neat way to describe the stress at a point. Three dimensions of stress. Stress in all three dimensions. Shear and normal stress is a nice way to organize that. In a way that's
Okay, so so like we're back to our kind of accounting idea, right? Like we can keep track of what the state of stress is at a given location, yes, and it's a description of that. Maybe another way to kind of think about it is at a given location and material, there are internal forces. You can still think of internal forces, and they're acting over very small microscopic areas. And what stresses are really doing is saying, hey, how are those internal forces, how are those internal moments, or internal loads, how do we describe what they're doing at an infinitesimally small load? And they're going to be dependent on the external loading, if it's a structure. Right? They're going to be dependent, they're also dependent on the geometry. And they can also vary within the structure. And they can, it's 3D. Right? We live in a 3D world with time. Okay? But if we're thinking about structure right now, we're talking about, okay, this is what that material is experiencing. You know, it could be like someone is trying to tear you apart or compress you, whatever they are, and you're trying to describe what that material is feeling, or what you're feeling as you're being pulled apart, stretched, twisted, whatever it is. And that is what we're trying to describe in a tensor. And there's a different state of stress, there's a different tensor at every location distributed to that material. And if you give me one tensor, that's all I need to know if I change my coordinate system, if I change my rotation, because it preserves that same. Okay, so those are maybe some ways to think about tensors, and some ways to think about state of stress. Okay, and this is how you would potentially write one of these tensors at a given location. Okay, and what's interesting is, you know, at every location you can write out an isotropic material, and it's elastic, and all these wonderful things, like simplified. Then you really only have 6 components that you're interested in. You have the sigma x, sigma y, sigma z, and then tau x, y, tau x, z. Those are the 6. And so there they are. Now so that's just a basic review of stress, really quickly. Anything else you want to talk about related to stress in mechanical solids? Any other thoughts, insights? We often use simplified geometries, and that's because our world is made of a lot of simplified geometries, and then we can think about how the state of stress relates to whether or not the material will fail. We spend a lot of time looking at transformations. And more circle is one way to describe those transformations. Even though the information is the same, when we have to compare it to criteria for failure that's been taken at a different orientation, we have to manipulate the state of stress so that we can see it and compare it accurately, for example, to uniaxial testing. So, how many of you are taking fluids right now? Right, wonderful. How many of you are already taking fluids? Right, wonderful. Okay. So, not just do 4 plus 5, but has to do 4 oranges plus 5 oranges equals how many oranges, right? 4 apples plus 5 oranges is equal to how many, how many fruit does John have? Okay. How many fruit does Abby have, or something like that, right? So let's go the opposite way. Tell me in English what this diagram in the upper right is describing. Not to say that my diagram is perfect, okay? But what is the scenario that we have described here in this image? Not exactly. Okay, but that is one of the special flows. Yes, that would be for a pipe, right?
Oh,
Now this is, but so let's take a look. What does this look like it's describing? Yes, Frank.
Liquid flowing over a horizontal plate.
Okay. Yeah. All right. So there's a horizontal plate, at least one of those. Okay. And okay. So okay, what else? What are you gonna say?
Fluid being shorn between two solid surfaces.
Shorn. Yes. Anyone watch Wallace and Gromit? Yeah. So they got some. I had not thought about sheep before you mentioned that.
Shear.
Yes. Yeah, no, I got it. I don't hear say it, but I like it. Well, I mean, if you've got shears on the sheep, it's kind of a similar thing, right? Shear stress is how shears work. That's right. And we talked about the mechanics of materials, right? That you reduce the gap, you get a lot of shear stress. So what does this mean here? Yeah.
One of these, the fluid is being like deformed.
Yeah, it's being sheared, right? Okay. How would you describe? So in English, what is this scenario describe? Okay, so we said shorn. We said material shorn. Okay, maybe we could be a little bit. Now let's be a little bit more engineering. What would be the experiment? How is this experiment set up? Shear our liquid. Yes. Sure. So yeah. So that's an interesting. Yes, this is at it is a fundamental aspect of lubrication theory. Okay, that essentially you have two moving surfaces and there's some small gap between them. And some, depending on who's teaching design mechanical components, you may get to lubrication theory, you may not get to lubrication. Okay. But yeah, so that we're on the right idea. This is essentially two parallel plates separated by a small distance with a fluid in between. Okay. And one of the bottom plate is stationary, and the top plate is moving at some velocity. Okay. And we're assuming that you have the no slip condition on the bottom plate and the no slip condition on the top plate. Okay. So that means that the particles at the bottom surface, the fluid particles right at the bottom surface, their velocity is 0. And the fluid particles on the top surface, they're going to be moving along that velocity. Does that describe this pretty well? So now, if I want to know the value of the shear stress, and where is the shear stress? I kind of threw it in there as this tau. What is the shear stress? And what is it across this gap, or in the space? What is the shear stress? Quadrant 3, we haven't heard from you much. No, 2, you're 2. You're quadrant 2. Quadrant 2. What's the shear stress that this fluid between these two plates is experiencing? and you're taking, or have taken fluid mechanics. Not to incriminate, but let's see. Quadrant, so like, you know, quadrant 2, what do you all say? Someone. Give me a shout. Alex, you're shaking your head. No. You've only got a couple of variables. Just start spitting out things that have those variables. Yes, Alex.
Shear strength.
Okay, that's an interesting observation. Okay, does the shear stress increase as you go from the bottom to the top? Okay. Well, maybe let's look at what is the definition of shear stress in a fluid. And that's there too, okay? Tau is equal to viscosity, right? That's the dynamic viscosity, mu. Pascal seconds, right? That's the viscosity. Times what? Says, I'm supposed to be in the K auditorium. Okay, no. I guess that's fine, all right? Oh no. I'm supposed to be in the fiber optics. Oh no. Okay, all right, so, what is this equation? It's mu times what? Okay, yes.
It's just viscosity times the velocity. The derivative of the velocity is y direction.
Okay, the derivative of the velocity, yes, the derivative of the velocity of the fluid, right, with respect to y. So this du dy is a derivative. Okay. And in this case, what does that derivative look like? Yes, Frank.
Like a straight line and constant.
Okay. Yes, it does. Okay, and what is its magnitude? Yes, thank you, right? So we're looking at essentially the slope of the velocity of the fluid with respect to y. Okay? What are our boundary conditions? Our boundary conditions are what? At the bottom, what's the velocity? 0. At the top, what's the velocity? U. There's a small gap, so we can assume that the velocity varies linearly, right? So it's 0 here, and it gets up to u at the top. Means if I go up halfway, if I go up halfway in between the bottom plate and the top plate, what is the velocity? Yeah, it's half, right? It's going to be halfway there. If I'm a quarter of the way up, it's a quarter of the velocity, the maximum velocity, right? If I'm 3/4 up, it's 3/4, or it's 3/4 of that velocity, right? And then I have my y, my height, right, that I'm interested in. So this du dy is just, what's your name? Kamari. You sent me messages. Okay, yes. Okay, so as Kamari has pointed out, that the slope of this velocity as a function of moving up in the y direction is just that that velocity of the top plate. And maybe I should have picked a different velocity. Maybe I should have picked it like V max or something. we're going to be simulating quite complicated problems in fluid mechanics. All right, and so this is just supposed to give us an introduction to what viscosity is. So, what are some viscous materials that you're familiar with? Okay, yes. Oil, all right? And it has a whole range of viscosities, right? Okay. What are some of your oil? What are your favorite types of oils? Mineral oil, okay? Typically low viscosity mineral oils. Yes? Olive oil. Yes, avocado oil. Lots of different oils. Silicone. I love the silicones, right? We talked about the silicones before. When we had those bubbles, and we were doing that material processing to get rid of the bubbles, that was essentially silicone oil that was cross-linking to then become silicone. Right? Until it had the cross-linker in it, was just silicone oil. Were you going to say something? Were you guys, you're all going to say something? Yeah? Okay? Water, right? Really pretty low viscosity. Air, even much lower viscosity, right? Okay, so you've got some ideas of what we're dealing with here. So this is just breaking it out. We have our boundary conditions here, which are saying, hey, at the top we have some velocity V naught. We have the gradient of velocity, okay, this gradient of u, and this kind of 2D problem, okay, but with unidirectional, one-directional flow with the plate. Okay, we can say that it's just going to be du dy. That's the V naught over the h. And the viscosity usually has units of pressure times time, so Pascal seconds qualifies. So you can say that the shear stress here is the mu times the gradient of the u. So this gradient of the u means that we can take kind of this unidirectional flow and begin to think about what happens in 2D and 3D. And so this is just talking this stuff over again. And now, instead of the material element, right, we have the fluid element, which is a material element, really. Okay? And we can think of what's happening to the stresses on this element. We can think of assigning a coordinate system, we can think of having a small length, and then we can think of it having a shear stress, as we see there, right? And then we have to have this element in equilibrium, so we put the stresses on it like that. Does this look familiar? Hopefully, yes. Okay. Any questions? Actually, I have a question for you though. So if I wanted to think about the forces involved here, or yeah, let's talk about force. Let's say I know the cross-sectional area of the top plate and the bottom plate. Now we talked about what's happening with fluids. What's happening, like now that you see this V naught, you see the U, you see all this stuff. What's happening? How much force do I have to apply to this plate on the top to get the velocity V naught? Because this is kind of important. We're going to end up looking, when we do our fluid simulations, we're going to end up thinking quite a bit about lift and drag on airfoils, on cylinders. But you're like, oh, but those are forces, and I got a fluid. So how do you go about bridging that gap here. How do you go about figuring out what the force, the drag force might be on a surface or on an object that's going through air or going through water? Yes?
Find the velocity.
Okay, so we need to know velocity, true. Okay, so I give you the velocity in this case. This is supposed to be a simplified case. So now you tell me, what is the force? And I say this plate has area. What's the force on the plate if I'm going at a particular velocity? And I'm purposely, when you do these simulations, you can do like steady state simulations and you can do transient simulations, right? And sometimes we'll do transient, sometimes we'll do steady state. When we talk about drag coefficients and lift coefficients, we're typically talking about steady state, right? It's like, give it at least a few seconds to kind of equilibrate, and now as they say, the flow is developed, and that's a steady state problem. So here, this is not an airfoil yet, but how do you go about figuring out the force that's being required that fluid is exerting on that top plate? Because that's essentially what drag is. Yes, Andrew. Okay, conservation momentum. All right. Yes, you can usually say conservation momentum and be right about things. True. I want an exact value though. Yes.
You have shear as a function of velocity gradient.
Okay, so what does that look like? What does that look like? I agree with you. Integrate over what, and what are you talking about? Okay, so what was that? I said, what did we say? The shear stress, is it constant everywhere in this problem, in the fluid? Yeah, it is, right? So then, what is that value? That is tau, all right? And that is the mu, the viscosity times u divided by h, or v naught, sorry. I know I was looking at the u, but yes, we have a v naught. So we have a v naught, so v naught over h times the mu, that's the shear stress. Times area, that's it. That's all we're going for, right? You've got the area that's experiencing the shear stress, and it's in the direction, right, of the x, right, and it's in the direction of v naught. So once you know that shear stress, then you can figure out the drag. Why is that relevant? Because that's literally the drag force. That's the force you have to drag this system on. We'll have more complicated profiles, right? But we're going to end up calculating shear stresses right on those surfaces and then integrating like you said. Okay. So this is like very basic. Well, it's an introduction or review of how you go about thinking about how viscosity affects a system. Now, this is assuming that this is a Newtonian fluid and it's laminar flow. And we said previously that the shear stress is equal to mu times the du dy. And that's for this flow in one direction. But if you have 2D flows, maybe you have a flow in u, right? And we're considering a y direction. And if you have flow so if you have flow u in the x direction, right? And you're looking at the y direction, right? That would be one. But you could also have a flow in the vertical direction, like a v, right? And be considering what's happening as you go xward, right? So your tau xy, right, which is considering both of these components, is actually the summation of the viscosity times these partial differentials of the x velocity u with respect to y, plus the partial velocity of the partial derivative of the y velocity with respect to x. And then, okay, and so you see that here we have this tau xy, the skin drag, all right, have these partials of u with respect to y, and partials of v with respect to x. Okay? And we can then expand that over to the 3D case on the right, where you have this matrix. Okay? What do you see there? You see, oh, I've got partial of u with respect to x. Is that going to create a shear stress? No. Someone said no, right? Because u and x are in the same direction. So that's not going to give you a shear stress. Partial of u with respect to y, does that give you a shear stress? Yes, because that's in the x direction velocity and the y direction. Right? They're orthogonal. And partial of u with respect to z, yes, that gives you a shear stress as well. It contributes to it. Okay? So you can think now in 3D that we can describe a tau xy, tau xz, tau xz, okay, the tau ij components, and it's going to be these combinations of the two corresponding derivatives, partial derivatives. Okay. Any questions on this? Any questions? And this, and then we have this other, and you have this compact tensor notation if you want. Okay. But what we want to get to is that mu is very important in terms of relating the gradients in the fluid flow to the shear stresses that we have in the fluids. Any comments, questions, concerns, ideas? Anyone watch these videos? They're really good, right? I don't know. They, I don't know. As the efficient engineer, I don't know if they are like, they've ever made their face public. No, they haven't. Okay. Kind of like the organic. Isn't the organic chemistry tutor? That's another one of them, right? They just have all these wonderful videos. Huh? Okay, yeah. So if you're interested in this, in like understanding viscosity in a very clear fashion, I do recommend this video. Okay. And I have another video too that you can watch too. Oh, okay. Now, someone tell me, what is the Reynolds number? And this will come up a lot in our simulations. When are you usually happy when you're working with a fluids problem? Yes?
Like 4,000, is it?
Yeah, so it depends. So this is a very good point. It depends on the configuration that you're dealing with, whether you're going to be turbulent or not. So, like in aircraft and air, in planes and stuff, right? We're talking about Reynolds numbers that are like hundreds of thousands. Okay, when you get to turbulence, right? And then, yeah, and then certain pipes and different things, you're going to be like looking at hundreds or thousands. Okay? A low Reynolds number, though, what does that mean? What does low Reynolds number mean?
Laminar flow.
Laminar flow, right? And high Reynolds number means turbulent flow. What is the Reynolds number, though, really? Like, what is it telling you? Yes?
Like a relationship between the viscous forces and like the other aspect.
Okay. How about inertia, right? Okay. So it's usually described as some type of density times velocity over viscosity, right? And so high Reynolds number means that you have a lot of inertia in your system, and viscosity is playing a lesser role. And when that happens, you have the opportunity for the kind of the flow to get a little bit disorganized, for lack of a better word, and start to induce vortices. And it doesn't necessarily have to follow the nice streamlines. Right? We have Bernoulli, right? And you have all those really nice streamlines that you're interested in maintaining. And a lot of times Bernoulli is really good, even at high Reynolds numbers. It can still help us out. But the idea here, at least far away from an object usually, the this number indicates why you would, when you're going to have to like start thinking about turbulence. When do you think about the Reynolds number? You ever think about the Reynolds number? You never think about the Reynolds number. Okay. Okay, yes, go ahead. And I can't remember, is it Bobby? No, what's your name? Bobby? Okay, yes, Bobby, go ahead.
When you're trying to create a realistic simulation or like a test.
Okay. Yeah, so depending on there will be different methods that we discuss in the class. Just like you have, this is analogous to, okay, in mechanics, right, this is a linear elastic material, this has an elastic modulus. Okay. That's a very nice model, very simple. Okay. And then if you've got laminar flow, you're doing Navier-Stokes, and Navier-Stokes is, well, it's good all the time. But you remember in Navier-Stokes, you could kind of make a lot of assumptions, and you start crossing off terms, knocking them out. When you get into turbulence, you have to use more complex models, and you have to hope that things are going to work out. We'll talk more about that. Okay, so like we were talking about, for high Reynolds number, the inertia dominates. For low Reynolds number, the viscosity dominates. Okay. And again, the efficient engineer comes into play here. If you want, spend a few minutes watching a video about Laminar.
This video from the Efficient Engineer is sponsored by...
Okay, there you go. Now, we can take different approaches to represent these particles. Sometimes you'll be thinking about, okay, I'm going to think about reference frames that are kind of attached to particles as they're moving, and other times you're going to think of fixed particle reference frames, fixed reference frames attached to the ground. And we are going to be able to think about them using nothing more than vector fields. Okay? So here we have velocity represented in a vector form based on some position in space and time. And we'll say that the velocity can have three directions. It can be in three directions. Acceleration, okay, is going to be this derivative that we see here with respect to time. And we can use the chain rule to introduce partial differential equations. So you see this? This is saying now, when I take a look at the velocity in the I direction or in X direction, right? I can break it down further and look at a partial, because I had to have some time component, okay? So if the U has a dependence on time, I better take a derivative with respect to it. And then I can break it up further and use the chain rule here and say, oh, I can also look at combinations in the X, combinations in the Y, and combinations in the Z. Okay? And so what you end up getting is this partial, this derivative, these partials that describe what you can call a total derivative of the velocity. Now, another way of writing this total derivative is to say you have the partial of the function for the velocity in a particular direction with respect to time plus this divergence, is v dot del times u. Okay? And so what you get there is, if you look at this operator, right, this is the velocity overall. and you're dotting it with this operator, and so you get this component. And that's the same. So this is just kind of a review of how you look at the calculations. Now, we can go further, okay, and look at the acceleration. Okay. So now we can kind of by extension say, okay, this was good for one component in one direction. I can look at the acceleration, which is comprising the total derivative of velocity versus time, and velocities in three directions, and then I can write it out. Now we have an acceleration. So this term right there, if the flow is steady, if we've reached a steady state and it's not changing in terms of time, then that term is going to be 0. And so that we can consider that local acceleration being 0. And this can be considered to be a convective acceleration, and this will be essentially just dependent on position, just dependent on geometry. So we're just kind of showing different ways of describing the velocities and the accelerations of particles. When you do your finite element analysis, or your finite volume analysis, better said, for this class, often we're not going to be, what do you think? What do you want to plot? If you have a fluids problem, what are you usually interested in? What are the quantity, what are the parameters you're interested in describing your system? Right, just imagine, you set up your geometry, you set everything up. What do you want it to tell you? Anyone in quadrant 3? Anyone in quadrant 3? Yeah, so you're really interested in figuring out the velocity fields. Okay? So this is going to help us understand what these velocity fields look like. And we're taking these derivatives and we're manipulating things like this. Okay? Now, we got these fields, and they have to satisfy what you're saying, momentum, and they also have to satisfy conservation of mass. Okay, so we introduced our first control volume. And spoiler alert, the finite volume method is using a bunch of control volumes. Okay? Just like the finite element analysis method discretizes problems in space into elements, they're really kind of like elements. They look exactly the same, graphically. They look like elements. We're going to call those volumes. Okay, so this is a control volume. And you remember that if you have a constant density, right, that you're going to have then this volume also has to be conserved. And so if you have a certain volume in, you've got to have a certain volume out. So that is something that's very, very important for the finite volume method. And using that in a few slides, you'll see that you can you don't have to use much math actually compared to the finite element method. You don't have to use much math, and it's very accurate. It can be very accurate. So that's why it's kind of popular. Okay, and then if we want to think of a summation or integral form of the mass conservation, okay, so we have a differential form. Remember, in fluid mechanics, you have the differential forms, and then you have the integral form. And assuming, right, that the density of the liquid is changing in this control volume, like we said, the output has to be fully then we can break it out in differential form. Then we can introduce this divergence of it's nice when the fluids are incompressible, right? You remember that? Air is often not incompressible. But for low enough speeds, you can kind of assume that air is compressed, that it's incompressible. If you can keep it compressible, that's kind of nice. Or keep it incompressible, that's kind of beneficial. And again, if you have this conservation of mass in place, which is often called continuity, then you can begin to break the problem into nice, how do you say it, parts that have kind of simple boundaries for the control volume, so that you have flow normal to that boundary, and you have then somewhere else also flow normal to that boundary, and the flow is, it's nice in that it's, pretty much all going normal to that boundary. So like in this case, you have maybe a nozzle and you have some velocity at the inlet times that cross-sectional area, a conservation of volume. We can say that the velocity of the outlet has to be equal times the area of the outlet has to be equal to that inlet times inlet velocity times the inlet area. Now, for momentum, okay, we have to think about the summation of forces, and we begin to think about essentially volumes and densities. If we think about volumes and densities, that gives us a mass, that gives us the inertial component. And what do we also need? We need an acceleration component. So acceleration would be some type of derivative of velocity. So that's what essentially you're seeing here, right? You're seeing velocity components with times density, right? So like rho times some type of v, and some derivative of that density, some derivative of that velocity. So rho times acceleration, right? And then you're seeing a volume component. So rho times volume is going to give you mass. So we start to see that we can develop some mass times acceleration components, and those are going to be forces. And if you think about momentum, sometimes we're thinking about mass times volume as well. So we can think about the stresses now acting on the surfaces of these control volumes. And that's another thing that we might be thinking about, right? We might want to know what the shear stress of the liquid is, in addition to understanding what the shear stress in the flows might be, or the pressures and the normal axial stresses as well. So, when you put all these things together, you get the beloved Navier-Stokes equation. All right, so we essentially have some gravitational components, we have some hydrostatic components, and we have some shear components. And that's going to be equal to inertia. This is essentially, right, the Newton's second law in fluid mechanics. And it's very profound in that it works for Newtonian liquids. Okay, so that gets us through kind of a review of fluid mechanics. Any questions? Any thoughts? Any hopes? Any dreams? Do you enjoy solving these fluid mechanics problems by hand? Yes, you do. Okay. Well, that's good. You'll be able to compare to ground truth. Right? So what are some of the ground truths that you might be able to use when you're doing simulations? Right? So I think in mechanics we have some pretty good ideas of what some of the ground truths are, but yes.
Like flow velocity of the balls.
Right, okay, so that's yes, you want your simulation to show that, right? If I'm interested in a more systems problem, right? So that's a boundary condition, which I agree with. What are some what can you take from your work in fluid mechanics and simulate to see if your simulation matches the analytical? So what are some of the example problems that you worked on in fluid mechanics? Okay, so yeah, pitot tubes. Okay, yeah, so that could be, so maybe something used to measure flow, right? And showing that, okay, if I stick this tube in there, I can have, for a given flow rate going past the tube, I have some type of pressure drop. Okay. Yeah, that could be an example. What are some other example problems? Yes, Frank.
Drag on cylinders.
Yeah, so drag on cylinders, which is what we're going to do, right? That's another example problem. Okay. A little bit more complicated. Okay. Other examples, like if you had to if you're like, hey, I just want to see if it matches my what I learned. I spent the whole semester studying fluid mechanics. I want to throw things in a simulation, and I want to see if it matches my analytical solutions. Yes.
Calculation of head loss.
Okay, head loss. All right, so in that case, right, you might have some tables, or you might have even just Bernoulli's, right? Depends on the problem, okay? Right? A pipe, you might have some ideas. Oh, we did that. Did I strike? No. You're like, okay. I thought you got excited about a pipe. I don't know. It's okay if you think you're excited about the pipe. Yeah. So you could also think about. You mentioned Poisson flow, right, earlier. Right? What is characteristic Poisson flow? Where you kind of have like this paraboloid, or you have a parabola flow. If it's a 2D pipe, or if it's a 3D pipe, you have parabola. Right? So you could start to look at these different fronts as well in a tube, in a pipe. That's what you get to do for your first example. All right? So you're going to be able to see, hey, look, this is what the pipe flow looks like. And you're going to be able to say, oh yeah, I remember doing this in fluid mechanics. And you're also going to be like, oh, I remember it was like 3 lines in fluid mechanics. And now I've got like a whole code that I have to run. All right? So there's some trade-offs here. Once again, we do look at baby steps. So if you can get it to work in a simple case, and you've got your model, you've got all your stuff in there, parameters, velocities, and it lines up, then you can start to make things a little more complicated. What's frustrating often is that real systems, you know, if you wanted to go through and try to make a whole like pipe for the plumbing in your house, that's probably not the best use of your time, first of all. Okay, but if you want to do that, you know, in simulation, that's going to take a long time, depending on how you simulate, right? But instead, we have things like Bernoulli's law, and we have different approximations that work very nicely for, you know, if you have an elbow and what the losses are on the elbow for the given flow rate and all these types of things. So the simulation, to be honest, is often a little bit limited in terms of what you can do versus the real world. Nonetheless, we'll end up doing things like airfoils, flows about cylinders and things like that, which are relevant to the real world and could allow you to say, okay, I got the baby step, and now I can do for real, like not for real, but I can do complicated things for a car company or an aerospace company that's interested in different objects. Or you could do your final project, right, which is going to be something that's relevant, hopefully. So in the last few minutes, let's talk about the finite volume method. Okay. So I like this figure. It gives a nice overview of what we try to do in finite element and finite volume methods. Okay, or in simulations in general, right? So we have to understand something about the physics and something about the domain over which we're doing our simulations. We need to know something about the equations that are going to govern. You know, what are some of the equations that we've covered up to this point in the class? What are some of the governing equations? It is. What have we studied? What physics have we been looking at up to this point? You have anyone? You have? Yeah, go ahead. Yeah, so the heat equation. What else? Anyone else? Huh? All right. What?
Velocity.
Okay, so we've been talking about velocity. What are the governing equations that affect velocity in different systems? Like, govern, what are the physics? You don't have to give me, not spit out exact equations, but what are the physics that we've been studying, right? Because one of the points of this class is that we kind of take one physics at a time and we learn how to simulate it. So I'm just asking you, you know, you go home this weekend or at the end of the semester and you talk to your family and I say, so you see you took the class on simulations. Like, what did you simulate? Yeah, Olivia. Yeah, so we talked about particle dynamics, particle physics, right? And I mean, not in the particle physics of colliding particles, what comes out, right? But we talked about particle dynamics. Yeah. We've talked about the heat equation, and talked about molecular interactions. We've even talked about how you can model particles bouncing off of walls, or particles bouncing into each other, right? So we've established these governing equations, and often it's the negative, the gradient of the potential functions that dictates some of that physics, right? Now we're getting into fluid flow. We're getting into the Navier-Stokes equations. We have to discretize our domain, okay? And that's, like we talked about, that's space, right? Sometimes we also have to discretize the equations we use. What is maybe the foremost example of discretizing our equations? Which method? Is like, it's almost like discretization is in the word, but it's not discretization, it's a different word. Fishing. Yeah, Bobby? Yeah, finite difference is like kind of the epitome of I am taking the derivative, which is generally a continuous function, and I am discretizing. It's even there. I didn't even, I gotta read. Yes, finite difference, finite volume, finite elements, okay? Boundary elements, yeah, different techniques there, okay? And then ultimately we get we get a system of algebraic equations. We invert that matrix, if that might be one of our approaches, right? Or we simulate them with the Euler method or relay, velocity relay method, and then we iterate and we get numerical solutions. So I like this. I think this graph kind of gives a nice overview of what we're trying to do in this class. And it's in this open. It's in this not open. I guess it's in the Springer Lake book. If you there's a whole book on finite volume, right? If you want to go home and read it. So we're just giving kind of the overview stuff. So once again, we're going to take a look at a problem, and in this case, this might be like a heat sink, and this is a microprocessor. So right, so there's some type of source, and then it's going in and it's heat sink, and somehow the heat is supposed to like go into this sink, right? Or maybe it's going into the fin system or something to dissipate into the environment. Okay, so we think of these steps, or they think of these steps, right? Where you have to have some type of domain. You have to have some governing equations, you have to do some discretization, and you have to solve, right? So here's the domain modeling. Here's the physics. Which equation is that? That's going to be, right, we got the heat equation there, essentially, right? We've got temperatures, okay? We've got a boundary condition, all these things. Then we discretize the domain, and then we come up with some interesting equations. And then we had to invert a matrix. That's to solve for the things that we care about right here. This is what we care about. This is the matrix that we have to invert and multiply times essentially this forcing function, right? The KT. So KT equals F. So let's look at this heat equation again, right? So often we're looking at steady state, which we've described before, right? And we've talked about what it looks like and the inversion of this matrix. Here is an example using the heat equation. And here's the heat equation. And once again, it's usually easier to take an element inside, right? Not on the borders. On the borders, right, you have to consider different boundary conditions. You have to make sure that you don't mess it up. Right? So let's take a look and see what's happening on this volume element right here. Number 9. That's where we're going to focus. So element number 9, 2D problem, has 4 walls, okay, 4 surfaces. And you probably can't see, but they're labeled like F1, F2, F3, F4. So those are the 4 faces. And we can think of using control volumes with this heat equation. And you can think of, oh, I'm just going to integrate both sides. And these are kind of like volume. This is a 2D element, but it's like a volume integral. You've got the control volume, and you can think, okay, this has got some finite depth into the page. So now we pull out something that I don't expect you to necessarily remember, called the divergence theorem, and it allows you to take a volume integral and express it in terms of a surface integral. Okay. And so the left side is experiencing this divergence theorem. Okay, so we go from the left side on the bottom left, where it's a volume integral, and now we have a surface integral. So dot ds, it was with respect to dv before, but now it's dot ds. And then we also look at the right side of the equation, and we're integrating over this volume, and we have a q dot on this volume. So that would be like a heat flux into the system times the volume of the element, and that's got to be equal what you see here. So now these are surface intervals. Well, that means that I got to apply them at each of these 4 surfaces. So these are nice orthogonal surfaces. So I'm going to do this integral in a discrete form. And I'm going to look at, okay, what is the k delta t? You know, left side in element, top, middle element, right, middle element, bottom, middle element, right? And we can look at that summation, so we discretize this integral relationship to a summation where you're looking at these faces 1 through 4 with this equation dotted with the surface 1, 2, 3, 4. Okay, so you see this is SF1, SF2, SF3, SF4. And how do we go about describing surfaces? Remember, we talked about particles before, bouncing off walls. We describe them with a normal direction and a location. In this case, we're just looking at the normal direction, and we're describing them with a length. Okay. So here, this SF1 on this side, right, that's got an I vector coming out, and it's got a length delta y. Okay. And SF2, same thing. It's got a length delta x, like this, F2 we can call it, the sign there, and it's in the j direction. So we can take these dot products. And what is this? This k delta t? This is just a gradient. How do you calculate a gradient discretely? I mean not discretely. Like it's not like, hey, you know, I want to discretely calculate your gradient. No, this is not something that you should use in your relationships with other people. Okay? But how do you calculate it? What do you do?
There's always some multi-dimensional, like things like those differences.
Yeah, right. It's a finite difference question, right? So we can break it down. Okay. This gradient, okay, can be thought of as some type of partial, right? And then we can use a first difference approximation, okay, and that comes out to be just a finite difference. All right. So now we've got a system, and there are these different components, but we start assembling, and maybe it's more clear over here. This is, you've got to look at the summation of the fluxes. And what are the summation of the fluxes? Well, volume has to be conserved. So if there's no heat flux into that element, then the summation of all those fluxes has to be equal to 0. All right? But if you have a heat flux in or out, right, then that's what it has to be equal to. So you assemble all those equations into a big K matrix, you invert it, and you try to solve. And this is essentially an example that's using a steady state problem. So the finite volume method is a method for representing partial differential equations. And it's similar to the finite element method. Okay? And there are opinions and facts that will compare. This is like the Eagles versus the Kansas City Chiefs. All right? They have different strengths and weaknesses. And, well, you can root for one or the other. Okay? But, again, but maybe what's different is that, I don't know, if you simulated the same problem, if you simulated the Chiefs and the Eagles playing each other, I guess you could probably have different winners. Okay? So some cases you want to use finite volume maybe, in other cases you want to use finite element. Unless you're COMSOL. If you're COMSOL, you say, no, you don't need this finite volume thing, just do finite element. It's the way most people do things. Right? But you saw how complicated the finite element method is. So finite volume actually has an easier setup usually, and it's accurate. So that's the benefit. So here's kind of some breakdowns in terms of when you might use the finite element method, and this is from COMSOL. All right. So they'll say finite element is essentially good for everything. Finite difference is good for some things. Finite volume is only good for a few things. All right? That's just how they put it out. So what is ANSYS's approach? We give you the whole kitchen sink, right? We already did. ANSYS will do finite element if you wanted to do it. But if you're doing fluids, they bought Fluent, and that's a finite volume method, right? That's what you're going to be doing. So anyway, today we've reviewed some aspects of mechanics, both fluid and solid, and we've introduced the finite volume method. We'll go for the attendance, and thank you for your time. Any questions?